So hello friends, welcome back to the lecture series of electronics measurement and instrumentation. In this lecture, I am going to discuss about true RMS meter. So basically true RMS meter, RMS is nothing but root mean square. So I think you are familiar with this concept, what is the RMS. So if any quantity is measured in terms of RMS, it means the peak value divided by under root, that is equal to the RMS value. So there exists a fundamental difference between the reading from a normal AC meter and on a true RMS meter. The first use the oscillatory movement with full or half wave rectifier and average the value of instantaneous rectify current. RMS meter, however, average the square of the instantaneous current value. That value is actually proportional to the instantaneous heating effect. This is the I am giving just an example. This scale up to RMS meter is calibrated in terms of square root of indicated current values. The result reading is therefore the square root of average of squared instantaneous value. So what is the true RMS reading? It is the square root of the average of the squared instantaneous input values, which is the RMS value of the measured AC current. A true RMS meter is always combination of normal mean value indicating meter and a squaring device whose output at any instant is proportional to the instantaneous squared input. It can be shown that AC component of the voltage developed across the common collector resistor of the two transistors that are connected in parallel and between the base of which a small AC voltage is applied is proportional to the square of applied input voltage. So that is the basically basics of this true RMS meter. See this particular circuit. So the circuit is used resistance in the 4.26. So it is called basically square device, and this square device is used for the designing of the true RMS meter. So here again, for the convert it into the multi-range, we use a different combination of the resistance. Then we use emitter follower transistor Q1, so that we have the high input impedance and low output resistance. Then a square circuit, we are already familiar in 4.26 it is given. Then again we use a squaring circuit, then our another circuit that's used for the measurement of the particular voltmeter. So the basic circuit employed two transistor is completed by the bridge arrangement, which DC component is cancelled out. So I hope you are familiar with this bridge arrangement, because here we take the difference of the two voltages, so the DC component is cancelled out. It is just our like our previous circuit used for the measurement of the voltmeter. One side of the bridge consists of two parallel connected transistors Q2 Q3, see here, and a common collector resistance R13. The side of the bridge employing P1 for bias setting is the basic squaring circuit. See this particular P1, this. So it is a basic squaring circuit employing P1 for basic setting is the bridge squaring circuit. The other side of the bridge is made of transistor Q4, whose base is biased by means of potentiometer. So other side of this, and we are familiar with this type of circuit. Here actually this transistor and this transistor combination, if you replace this part, so we have already studied about measurement of the voltage. Then they inserted this particular circuit because here we required to measure RMS value, and then this particular arrangement. So these both are actually inserted in an emitter follower circuit, are the differential amplifier combination. In the differential amplifier combination we use this Q1 Q4. So between this Q1 Q4 we insert this particular circuit that is used for squaring circuit. Here 4.26 they have also given the same circuit. So this particular P1 potentiometer P1 base bias voltage of squaring circuit that can be adjusted for symmetrical operation of transistor Q2 and Q3. See here, this particular transistor is even Q1 Q4 is symmetrical, Q2 Q3 is symmetrical. To maintain this symmetry, what they try to achieve, make P1 is equal to 0. Similarly, potentiometer P2 must be set for 0 input signal. The bridge is balanced. Similarly, this bridge is, if you make this bridge balanced bridge combination, to make this balance, this particular bridge is balanced, again to make this is also equal to 0. So sorry, it is the P3, here P2 is in the side, that is the P1, that is the P2. Again that is used for the bridge balance circuit. Then transistor Q1 is used to improve the temperature stability of the whole circuit, which is basically obtained by emitter resistance. It is a basically emitter follower combination, nothing else, this particular Q1. So it provides a temperature stability plus high input impedance, low output impedance. The low current through Q2, Q3, Q4 require large emitter resistance value to fulfill the condition. Similarly, it requires the large emitter resistance, and we know that the Q1 have high input impedance and low output impedance. Then we use this particular combination to make this input high. So Q2, Q3, Q4 require large emitter resistance value to fulfill the condition for compensation. Therefore, another transistor Q1 have been added to compensate the temperature change of Q2 and Q3. This particular we have added. Okay. This particular combination is used so that this particular provide temperature stability. It provide emitter follower combination. So that are the basically advantage. The bias on this transistor has to be adjusted by selecting appropriate value of R8 and R9. That all this combination is used for the biasing, and we know. See this particular, what is the value of R8 and R9, R8 and R9. So it is basically a potential divider combination. So that potential divider combination is connected to the base of transistor Q1. So if you vary this, then the IB will change, so the base current will change, so this bias will change. So that is basically it is also simple potential divider bias combination is used. The input of the squaring device is connected to the voltage divider that is calibrated in 7 range, namely this. So that is all about this. Then, as the name suggests, the true RMS responding AC voltmeter responds to the true RMS value. That is basically the another circuit. This voltmeter measure RMS value of AC voltage. Circuit diagram of true RMS responding AC voltmeter is shown in figure. Here we see there the two thermocouple, and one and it is connected in such a way that it's form a bridge. So once the with the help of balance and unbalance of the bridge, we are able to measure the voltages. See this working of the above circuit consists of AC amplifier, two thermocouple, DC amplifier, and PMMC galvanometer. Basically, this particular AC amplifier, then it is connected to a thermocouple. This thermocouple converts this AC to the DC, so the DC is measured by PMMC instrument, and this whole circuit is form a bridge. So the sensitivity is very high. Two thermocouple are used in the above circuit are measuring thermocouple and a balancing thermocouple. Measuring thermocouple produce output voltage which is proportional to the RMS value of the AC voltage signal. Any thermocouple convert a square of the input quantity into a normal quantity. This means there exists a non-linear relationship between output and input of the thermocouple. The effect of non-linear behavior of the thermocouple can be neglected by using another thermocouple in the feedback, so that this particular feedback circuit actually form a bridge. This thermocouple that is used for this purpose is known as balancing bridge. The two thermocouple, namely measuring thermocouple and balancing thermocouple, together form a bridge at the input DC amplifier. As a result, the meter always respond to the true RMS value of AC voltage signal. So that is the basically advantage of this type of the circuit. Then so that's all about the AC voltmeter. In the next class we are going to discuss about a digital voltmeter. So thanks for your kind attention.